Hello dear students, welcome to the course of Thermodynamics 1. Today we are going to discuss about various non-flow processes. Myself Mistry, Assistant Professor from Mechanical Department of LJIET Institute of Engineering and Technology. So let's start with the discussion. So the very first process that we will observe today is constant volume process or isochoric process. Constant volume means what? The volume of the chamber or vessel throughout the process will remain constant. Another name is isochoric process. Okay, so you have to remember these two names. It is very important. Okay, so let's understand this particularly. So first of all, we will understand the presentation of this process on PV diagram. Okay, we will follow this convention for all different processes that we are going to discuss in this particular chapter. So the first convention is what? We will see the process on PV diagram. Okay, so in order to understand this PV diagram, let's take this particular image that is shown in the figure here. So you can see that the volume is constant. Okay, so the volume of this particular chamber is constant. Okay, and you can see over here the stove is supplying the heat. So as you will supply the heat, you can see the particular heat portion is getting red. So whenever the stove is supplying some heat, then here what will happen? Because the volume is constant, so there will not be any change in the property of the volume. But as soon as you will supply the heat, then obviously the pressure inside this chamber will increase and also the temperature inside the chamber will increase. You can appreciate these two facts with the help of this particular devices. You can observe that this pressure indicator is showing the increase in the pressure as soon as we will supply this heat. See, this heat is supplied and this pressure is increasing. Okay, simultaneously you can also observe and appreciate the fact that the temperature that is shown by this particular temperature indicator is also increasing. See over here, right? So the temperature is also increasing as soon as we will supply the heat. Now using this particular understanding, let's plot the PV diagram. So as you can see, initially, let's say the initial state, let's say at t is equal to 0 time, or let's say at 9 AM in the morning, the pressure inside this chamber is at this particular state, that is 1. So this particular pressure will be called as P1. Okay, and the volume is constant, so it is called as V1. Okay, this is V1 volume. Remember students that volume is taken on x-axis and pressure is taken on y-axis. Now as soon as we will supply the heat, and after let's say 1 minute, let's say 9 and 1 AM, 9 hour and 1 minute AM. Okay, so 9:01 AM, the state is 2. Okay, so at this particular 2 state, the pressure will be denoted by P2. Okay, and you will appreciate that the volume has not changed because the volume is constant. So that is why the line joining from 1 to 2 will be a straight vertical line. So for 2 or for 1, the value of volume on the x-axis will remain same. But for 1 and 2, the value of pressure on the y-axis will change and it will increase. You can appreciate that, right? I hope you are clear up to this point. Further, now work done during this process. So you know that in our previous discussion we have already told that whenever you are not changing any volume, then the work done will be 0. Okay, so here you can see that W is equal to PdV, integration of PdV from V1 to V2. Here change in volume is 0. That is why you can say and appreciate that the dV is 0. So you multiply P with 0. So you will get the value of 0. So the work done over here is 0. Okay, I hope you are clear up to this point. Now relation between PV and T, that is pressure, volume and temperature. So what is the relation between pressure, volume and temperature? So simple. Here you can write that this is the generalized form, that is combination of Boyle's, Charles and Gay-Lussac law, that is P1 V1 by T1 is equal to P2 V2 by T2. You can write this form for any gas, right? So P1 V1 by T1 is equal to P2 V2 by T2. Here you can appreciate that V1 and V2 is same. So V1 and V2 will be cancelled out. So pressure P1 by temperature T1 is equal to P2 by T2, right? So also you can say that pressure is proportional to temperature when volume is constant, right? You can identify which law is this, whether is it Boyle's, Charles or Gay-Lussac. Okay, you can recall that. So that is the relation between this P, V and T. Now change in internal energy. So what will be the change in internal energy? Simple. Internal energy is delta U, and you can say that we have already discussed that delta U is nothing but CV delta T, right? That was for unit mass. But if we do not have unit mass, and if we have m mass, so you can write mCV delta T or dt, mCV dt, right? The temperature range is T1 to T2, right? So what you can write is U2 minus U1 is equal to, you do the integration of dt, so it will be T, and the limits are T1 to T2, so that is why T2 minus T. So that will be the change in internal energy during this particular process. Okay. Further, heat transfer. So heat transfer will be equal to what? Q is equal to delta U plus W. You know that according to the first law of thermodynamics. Here W is equal to 0, work done is 0. So whatever the change in internal energy is there, the same will be the heat supply. Okay, so heat supply will be equivalent to delta U, and value of delta U is already known to us, that is mCV T2 minus T1. I hope you are able to grasp this. Okay, now change in enthalpy. Very simple. Enthalpy change is what? So at initial state, let's say the enthalpy H1 is equal to U1 plus P1 V1, and at second state the enthalpy H2 is equal to U2 plus P2 V2. Okay, now what we can do is change in enthalpy. So we will subtract H2 minus H1. Okay, so substitute the value of H2 over here, so you can write U2 plus P2 V2 minus H1 over here, U1 plus P1 V1. You can take U2 U1 terms on same bracket, in same bracket, and you can take P2 V2 and P1 V1 term in same bracket. Okay, so let's do that. So we can do like this: U2 minus U1 plus P2 V2 minus P1 V2. Okay, so here you may appreciate that pressure PV is equal to mRT2 according to characteristic gas equation, right? And P1 V1 is equal to mRT1. So instead of P2 V2 you can write mRT2, and instead of P1 V1 you can write mRT1. Substitute these two values over here. So what we will get is mCV T2 minus T1 plus mRT2 minus T1. Now you might be having doubt, sir, instead of this U2 minus U1, what you have written? So recall that change in internal energy is nothing but mCV T2 minus T1. We have already derived over here, right? That is why it is written over here. Instead of U2 minus U1, we have written mCV T2 minus T1, and instead of P2 V2 minus P1 V1, we have written mR T2 minus T1. Here you can appreciate the mR is constant in these two terms, so it is taken outside of the bracket, right? Further, so this is all about the constant volume process or isochoric process. So now we will follow this same convention for all the processes. Okay, basically there are 5 processes in this chapter. Okay, so first we have seen constant volume process or isochoric process. You have to remember the results of every aspect. Okay, what is the amount of heat transfer during the isochoric process, what is the change in enthalpy, what is the, let's say, relation between PV and T, what is the work done during the process. So you have to remember all these points. Okay, now constant pressure process or isobaric process. Remember the other name also, constant pressure is also known as isobaric process. Now representation of PV diagram is shown over here. Pressure is constant. Okay, so pressure is on y-axis and volume is on x-axis. So if you want to keep the pressure constant, then obviously the line will be straight horizontal line. So here it will be one state, here it will be second state. Okay, So for both this state, you can appreciate that the pressure will be same, that is equal to P1, or that will be equal to, but the volume will get changed. Okay, so let's understand that how this will occur. So understand this particular figure. As you can see, that pressure is constant. We have already discussed this during the Boyle's law, Charles law, Gay-Lussac law, right? This particular processes. Okay, but in different manner. Okay, but the same thing is happening over here. The concept is same. Okay, so here let's understand this. In this vessel, whenever you are supplying the heat, okay, so what will happen initially? If the piston is not moving, then the pressure will increase. But if you want to keep the pressure constant, then you have to increase the volume. So that is why you can observe over here that the volume is increasing, but the pressure indicator is showing the same pressure. Okay, because the amount of heat that you have added, so that amount of heat is accompanied by increasing the volume. Okay, so that is how this will work. Okay, obviously the temperature will rise. Okay, so that is how this will take place. So initially your volume will be V1, finally your volume will be V2. So you can appreciate over here also V1 and V2, but the pressure will remain same. So now what will be the work done? The work done will be very simple. W is equal to integration P dV. So you integrate that. Here the volume is not constant, so your value will be P into V2 minus V1. This will be the work done. Now next will be what? Relation between PVT. So relation between PVT will be what? You can write P1 V1 by T1 is equal to P2 V2 by T2. Now here P1 and P2 are same, so you can neglect P1 and P2. So what we are left with, P1 by T1 is equal to P2 by T2. Okay, this is the relation between pressure, volume and temperature. That volume is proportional to temperature when the pressure is constant. Okay, you can appreciate from here also, right students? If the volume is increasing, then the temperature indicator is also showing increase in the temperature. Okay, and if the volume is decreasing, then the temperature indicator shows us the decrease in the temperature, right? So you can appreciate that the volume is proportional to temperature during the constant pressure process. Further, change in internal energy. Now change in internal energy, that is delta U, is equal to what? mCv T2 minus T1. Now further, that is already known to us, right? We have derived that earlier. Now further, heat transfer. So heat transfer is equal to what? Heat transfer is equal to Q is equal to delta U plus W. Now delta U, we know that mCv T2 minus T1 plus W, that is PV2 minus P1. Now mCv T2 minus T1, PV2 minus V1, we can write MR T2 minus T1. We have followed this practice in the previous process also, so you are now very well aware, right? Now you can take M as the common, so M is taken as common. So what we can write T2 minus T1, and what we are left with CV plus R. So we are left with CV plus R. Now CV plus R, so if you remember and recall, then Cp minus Cv equal to R. So if you make Cp as a subject and you take Cv on the other side of the equal to sign, then you can write R plus Cv. So instead of this R plus Cv, we can write Cp directly. So that is why mCp T2 minus T1 is written. That is equal to heat transfer Q. Okay, so that is the heat transfer during the constant pressure process. Further, change in enthalpy. Now change in enthalpy is what? So delta H is equal to mCp T2 minus T1. So today we are going to keep up to this point. Thank you.